this video, we're going to go over the Unit 8 free response question examples. Some of these are calculator questions and some of them are not calculator, but all of them I will work without the use of the calculator just so you can see how that would be done. Because on this year's test, you won't be really required to use that calculator for any reason. All problems are made and written such that you can work them without a calculator. All the work can be done by hand. So I try to pull problems from a lot of different concepts since Unit 8 has a lot to do with area and volume, and you have a lot of different orientations and a lot of different types of cross sections that you could use. So I try to pull as much as I could so that you can see a wide variety of problems worked. Okay, so this first problem gives us the graph of f of x and g of x, and we need to let the region R is bounded in between here, between the two graphs here and here. So what we need to do is we need to first figure out which of these graphs is the top and which one of these graphs is the bottom, because if you look at this problem, it's a top minus bottom problem. This graph up here is always on top or above, vertically above the graph of this one down here. So I first need to figure out which graph is which. So the way I can do that without a calculator is by plugging in a point. And based on this graph, or based on these coordinates, it looks like my x-axis only goes up until 2 before the region ends. So maybe I should try plugging in a 1. If I try plugging in a 1 right here, maybe that'll tell me, hopefully maybe this point is 1. It doesn't say it explicitly. But let me go ahead and plug in a 1. So 2 times 1 is 2, minus 6 plus 4. So 2 minus 6 is negative 4 plus 4 is 0. Looks like it's got to be this guy right here. So that's a really quick way to check that graph down there is f of x, because we found that the value at 1 is equal to 0. X equals 1 and gives me 0. So this bottom graph, I'll highlight it in purple. That graph is f of x. And then that tells me that this top graph, I'll highlight it in blue, is g of x. All right, so we got g of x is above f of x. We need to first find the area of R. Let's go ahead and I'll put the work right here, the area of R. So to find the area, we need to integrate from the beginning to the end of this region. Meaning, if this is a top minus bottom, that means this is a graph in terms of x. All my equations are in terms of x. Top minus bottom is in terms of x. So that means my bounds also need to be x values. So it looks like it starts at 0, the region, and it ends at 2, 0 to 2. So those are going to be my bounds of integration here, 0 to 2. And then this is where I need to do my top minus bottom. So we're going to put g of x minus f of x here. So I got 4 cosine 1/4 pi x. So there's g of x minus f of x. Minus, make sure you put parentheses here, okay? Because all of this is being subtracted together. So that minus has to be distributed to all of them, all the terms. 2x squared minus 6x plus 4, all in parentheses. Close that parentheses, ending my integrand. And I have a dx at the end to show that I've finished what I'm integrating. Okay. So part B is important to read the whole problem. A lot of times people don't read the entire problem and then they do more work than is necessary, hence they waste their time. That's another reason why you may not score well on a test, is because you don't use your time wisely or you don't read the problem. These first 5 words are very important. Write, but do not evaluate. That means write something down, but don't find the answer. Write, but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 4. So let's think about what this means. We want to revolve this guy around the line y equals 4. So let's first draw the line y equals 4. It's up here. Y equals 4. And what is happening is this entire region is being rotated around this right here. Okay, so now what I'm going to do is I'm going to highlight this guy right here. The reason I highlighted that gray was because it's airspace. When I revolve R around y equals 4, this stuff right here is air. And so if I were to kind of draw or sketch what it looks like on the other side, there's the blue highlighted graph reflected, and then there's the purple graph reflected. So if I think about the way this shape looks, it's kind of like if you were to look inside of it here, there would be space right here, open space, air, space right here. This stuff is solid and it's going around this line. So this is called a washer method, because if I were to draw one of my rectangles inside of here that's being revolved, it's going to show you the picture of a washer. It's kind of hard to see in there, but this little circle right here is empty. There's no area in there. There's nothing right there. It's empty. It's space. Whereas this stuff is solid material that's being revolved. So this is a washer method. So now I'm going to erase all this nonsense right here and just show you what's important. That was just to kind of get a visual understanding. So what's happening is I'm going to draw two different things on this picture. I'm going to draw this line right here, this red one, and I'm going to draw this green one. Okay, the red line is going until the blue highlighted graph, and the green line is going until the purple highlighted graph. So if I were to think about this as a disk method, I would be creating disks out of these guys. And what's happening is I'm taking this bigger radius. If I were to circle it around y equals 4, this green line would represent a radius, and so would this red one. But remember, I don't want any area in here. I don't want any of this space to be integrated. I'm just looking at region R. So what I'm doing is I'm subtracting out this space in here out from inside of this three-dimensional shape. So a washer method is essentially two different disk methods. The way we can set this up is we have our integral still from 0 to 2, but now we need to think about what is the bigger radius. The bigger radius here is this green one. And at the top I see a 4. And furthest away I see f of x. So what I can do here is first put 4 minus f of x. That will give me the distance between the line y equals 4 and the purple line here. 4 minus f of x does that. Top minus bottom. The principle still holds of top minus bottom. And since I'm revolving it around the x-axis, I'm going to square it. And the reason I'm squaring it is because this is representing the radius. And anytime I want to take the area of a circle, I do pi r squared. So I have r squared. I just need to tack on a pi in front right here. So I got pi r squared right there. But this does not give me the area or the volume of the volume that I'm looking for. It's giving me the volume of everything between the graph of f and the line 4. I want to remove the stuff that's in between the line y equals 4 and the graph g of x as well. I want to remove that. So I need to subtract that piece out. And it's going to look very similar to this first term we wrote up here. But instead of writing 4 minus f of x, it's going to be 4 minus g of x, because that's the distance between 4 and g of x here on this graph. So the reason why I squared this guy now is because this is a different radius, and I need to square it. I need to subtract it out, and I factored out this pi right here. I'm going to put the pi in front of the entire integral, because this would essentially be the same thing as writing another integral right here and putting a pi there. and going from 0 to 2. This is also a correct answer, but I'm going to factor that pi and the integral out right there and put the dx at the end, and I'm integrating all of this together. And there's your expression. You don't need to do any further work because the problem tells us just to write but do not evaluate. All right, let's keep going. All right, this is another problem that's asking a few different things that involve area and volume. I'm not going to work part A because I just did an area problem where we do top minus bottom. This problem, however, could be done as right minus left as well. You would get the same answer either way. But you can work that out on your own and check the key on the AP website. It'll show you both of the solutions. Regardless of whether you did it in terms of X or did it in terms of Y, you'll get the answer. You'll still get the same answer. Okay, on this problem, I want to focus on part B here because this part is asking us about cross sections. So the first thing we need to identify is what are the cross sections perpendicular to? They're perpendicular to the x-axis. So that means that I want to draw my lines inside of this region perpendicular to the x-axis like that. Okay, x-axis goes horizontally, perpendicular would be vertically oriented lines. So my cross sections look like this. So what you want to think of this shape right here is if you think about if you're baking a loaf of bread, the pan is flat at the bottom, just like this paper or your screen is flat here. And what's happening when you bake bread is it rises up out of the pan in some particular shape. For this problem, it's telling us that each slice of this weirdly shaped loaf of bread rises and creates an area of sine of pi over 2x. At every single particular point, you might have a different area because your area is in terms of x. Okay, but this equation right here tells me the area of one specific slice. If I were to make a cut somewhere inside of this interval and look at the piece of bread from the side and I calculated its area, it would be this value right here. So I need to first set up an integral and find the volume of that solid here. So what this is going to be, okay, it's going to be an integral. And since my graph is in terms of x, okay, I'm perpendicular to the x-axis, I need to use the x values as my bounds, 0 to positive 2, 0 to 2. I'll put that this is part B. Integrating from 0 to 2. And what I want to do is I want to integrate this guy right here. Because what that means is I'm integrating from 0 to 2. I'm adding up every single particular x value in between there, evaluated at sine of pi over 2x. Okay, sine of pi over 2x represents the area at one slice. I want the area of all of these slices added up together between 0 and 2. So this integral, what that does, this integral is saying add up all of these slices that have an area of sine of pi over 2 between 0 and 2. Add all of those up together. That's what this integral can be interpreted as. And so we need to, this was number 4 from 2009. It should be able to be done without a calculator. So let's go ahead and integrate this guy. The antiderivative of cosine, the antiderivative of sine is negative cosine pi over 2 times x. But since this is something other than x and it has just an x to the power of 1, I need to divide by pi over 2. And I'm going to evaluate this from 0 to 2. So first let's plug in the 2. I got negative cosine of pi over 2 times 2 is just negative cosine of pi divided by pi over 2. And I have minus Now we need to plug in the lower bound, 0, minus negative cosine of pi over 2 times 0 is just 0 over pi over 2. Okay, I need to simplify this now. So cosine of pi is going to be -1. If you think about your unit circle, cosine of pi is -1 times the negative is +1. And then I have 1 over pi over 2, or that's the same thing as the reciprocal of 2 over pi. Then I have minus and negative, so that makes this a plus. And then cosine of 0 is also 1. So plus 1 over pi over 2, which is 2 over pi, the reciprocal again. And I would leave it like this. If you're not sure how to add these two together, they have a common denominator. This is 4 over pi. Or you could just leave it like this and not waste time writing the 4 over pi. Either the way it works. All right, let's set up part C here. All right, part C now is very similar. It's cross sections again, but it's saying this time the cross sections are perpendicular to the y-axis and they're squares. So let me go ahead and erase those blue cross sections that I drew. This time for part C, my cross sections are perpendicular to the y-axis. So let me draw my lines going this way now, perpendicular to the y-axis. Okay, now if you still think about this, you have a pan, it's flat at the bottom, the loaf is rising when you bake it, but when you make the cuts after you bake the bread, the cuts are going this way. Okay, and when you make those cuts, each slice is going to be a perfect square. Each slice is a perfect square. So I need to write, but do not evaluate. So I just need to set this one up. I don't need to evaluate or integrate or anything else like that. This time when I integrate, since I'm perpendicular to the y-axis, all of my terms and values in my integral have to be in terms of y. So I'm going to start from 0, but go on my y-axis up to 4. So I'm integrating from 0 to 4. And now what I want to do is I want to figure out what is my right and what is my left. If you look at your study guide, when you have an integral in terms of y, you want to do right minus left. So the right graph here is this parabola y equals x squared. Now I can't write this as x squared in my integral because I need it to be in terms of y. So instead of y equals x squared, that's the same thing as x equals the square root of y. Same thing for my other graph, y equals 2x. Instead of putting y equals 2x, it's going to be x equals 1/2 y, or y over 2. So square root of y is my right side, and 1/2 y is my left side. So all I need to go down here and do is put those in. Right minus the left. So I'm finding the volume when the cross sections are squares. So the formula for a square, if you look on your formula chart again, is side squared. This distance, or this expression right here, gives me the distance between the two graphs, which is also the bottom of a square. The base of the square and its height are the same thing. So to get an area of one square, I would square it, and to add all of the squares in this interval up together, I would integrate it. And then I would tack on a dy at the end there. There it is. There's your integral setup. Okay, let's keep moving ahead. Okay, this one says find the sum of the areas of regions R and S for part A. Okay, I'm not going to work that part because I'm confident that you can find the area of each of these guys. This was a calculator problem, so um, you can use your calculator to integrate these, just type them in. This would be a math 9 where you would type in the integrals. You would need to find the intersection here though. Integrate this first piece, integrate the second piece, top minus bottom, then top minus bottom. Keep in mind that the two graphs switch positions, and then you would have to add those two up separately. Part B here is what I'm going to work. It says the cross sections are squares, and these are perpendicular to the x-axis. And we're just focused on region S, just like that. Perpendicular to the x-axis, find the volume of this solid of region S. So here we would first need to figure out by graphing which graph is which. I believe f of x is this guy right here, and g of x is this guy down here. If I want to find the area of one of these squares, I would have to do top minus bottom. And since this is a calculator problem, you could just write f of x minus g of x instead of writing the entire function out. F of x minus g of x. Since that's the base of the square, squaring it would give me the area of a square. It's in terms of x, so I put a dx. And I would need to go back. I don't have my calculator with me right now, but you would go and find this x coordinate right here. And you know this x coordinate right here is a 2. I believe I've worked this problem before, and it's like 1 point something. So I'm not going to write the value down. Let's just say that this is some value, and I'm going to call it a. So you'd integrate from a to 2. And that gives you the expression to set up finding the area of those, the volume of this solid. And it gives you some value. Be sure to round properly if you're using your calculator. But on this year's test, you're not expected to work any problem that's requiring a calculator. Most of them, or all of them, will be questions that you can do and integrate without a calculator. So this is something you'd have to do in your calculator here. Okay, this one is talking about an isosceles right triangle. So let's first think about an isosceles right triangle. An isosceles right triangle is a triangle that but is a triangle that has two congruent sides, and it's a right triangle, so you have a right angle connecting the two congruent sides. But this problem says that one of the legs is in R, meaning if I'm perpendicular to the x-axis, if the cross sections are perpendicular to the x-axis, then what you can think about is, if I think about the bottom of this pan, the bottom is like this, and my isosceles right triangle is like that. So it's still the same shape, but it's just reoriented so that the base is here. So if I think about the area of this shape, the area is 1/2 base times height. Well, the base times the height is it's the same thing as saying the base times itself, because they're congruent. So I'm going to put 1/2 base squared for this one. So what we need to figure out now is, what is the distance of the base for this region R? Well, it's top minus bottom here. If I see the straight line, it's always above, vertically above the bottom function. So top minus bottom. So the bottom here is f of x, and the top is y equals 4. So let's set up this integral. I'll let you solve it, but I just want to show you the setup just so you know that you're on the right track. So part B here, It's going to be the integral from, and I would need to find the intersections of these two. It looks like it intersects starting at 0 and then intersects somewhere here. Let's just call that point A, and let me name it another point, point C, because I already used B as the base. So I would integrate from A to C, whatever those values are, these two intersections, the x coordinates of those. And I would put this template inside of my integral right here. 1/2 something squared. Well, that something squared is the distance between the two graphs, top minus bottom. It's going to be 4 minus f of x as the base. 4 minus f of x. Put a dx on the outside. Okay, this was also a calculator problem number 2, but on your AP test this year, you won't be required to do any problems where the functions are complicated. The functions will be such that you can integrate them. You could actually integrate this and get a numerical expression. It's just power rules here. But I'm not going to spend too much time getting the decimal value here. I just want you to focus on this expression, and then the rest you can, I know, you can integrate that. Okay. Here we have for 2010 number 4, we have part B and C. For part B, we just need to write but not evaluate. This volume is going to be revolved around the horizontal line y equals 7. So if you notice, this line right here is actually y equals 6, because the straight horizontal line is y equals 6. Y equals 7 is 1 unit above that. So that means this whole thing is being revolved around. Okay, you see this airspace inside of here. So this is a washer method. And I'm integrating, and my integral is going to be in terms of x. So I think about this expression. The integral is from 0 to 6 because I'm starting here and going this way until 6. And I'm going to once again shade in or draw in the larger distance and the shorter distance. Okay, the longer distance is always going to be 7 minus this graph right here, which is 2 squared root of x. Ah. 7 minus 2 squared of x goes first. 7 minus 2 root x, pi, and the squared pi r squared. But then I need to subtract out this airspace inside of here when I revolve that. So actually, if you think about this being revolved around this straight line, it's creating a cylinder, and we're carving that cylinder out. So I need to subtract out 7 minus 6 squared, because 7 is above 6, 7 minus 6, and then I square it, giving me the formula for pi r squared. So this is the smaller shape being subtracted out of this larger. And this is going to be dx at the end. There's your expression. Okay, we have this base region R, and we have cross sections that are perpendicular to the y-axis, are rectangles whose height is 3 times the length. Okay, so it's giving you specific information, 3 times the length of its base. So what that means is if I draw one rectangle standing upright, it says the rectangle has height that's 3 times the length of the base. So that let's say that this guy down here is base, then that means this is 3 times the base, because it's saying 3 times the length of its base. Okay, so in order to find the area of this guy, the area of this guy would be base times height, or 3b squared. 3b times b is 3b squared. So we need to figure out what is b, what is the distance between the two sides of the base. If we're oriented perpendicular to the y-axis, I'll go up here. I'm perpendicular to the y-axis going this way. So it's right minus left. The right side minus the left side. So I need to change my graph to be in terms of y. If I have y equals square root of 2x, that's the same thing as x is equal to, let's see, y over 2, all of that squared. And this side over here, the left, is just x equals 0, the vertical line x equals 0. So let me focus on this guy right here, and this guy right here. So the base of a rectangle is the difference between x equals y over 2 squared minus x equals 0. So my base is just essentially this guy right here. So I just need to find an integral expression. I don't need to evaluate here. Just need to write the integral expression. So I'm going to integrate. Since I'm in terms of y, my bounds have to be in terms of y from 0 to 6. 0 to 6. And I need to write in this template right here, 3b squared. 3 times something squared, and I'm in terms of y, so dy at the end. We've got right minus left. So there's the right, y over 2 squared minus the left, which is 0. There's your integral expression. Okay, I'm writing in that minus 0 because if your axis was something other than that, you would still have to put minus whatever that value is. All right, last problem. This is another small topic that was in Unit 8. It's the average value. Okay, it's asking you to find the average value. If you ever see this word average value, this is not the same thing as average rate of change. That's completely different. Average value is the area under the curve divided by how many x coordinates, or the difference between your x coordinates. So in a nutshell, your average value is 1 over b minus a times the integral from a to b of whatever you're finding the average value of. It's asking for the average value of the radius. So here's your radius right here. So put 1 over 20, 3 plus h squared dh. The variable is h. 0 to 10. So my bounds a and b are 0 and 10. 0 to 10. B minus a is 10 minus 0. All right, my voice is getting tired, so I'm going to stop right here. This is the last problem. So finding that value, you could do that in the calculator. But if you have any questions, please let me know. I'm here for whatever help you might need.